Hi everyone, welcome to topic 6.3, hypothesis testing for paired samples and matched sample tests. Again, let's distinguish between one sample and two sample tests. So for a one sample test, we are comparing our sample mean to our hypothesized population parameter. For independent sample tests, we compare the mean of two different groups. A research question for a paired test may be, is the weight loss program effective? This is a before and after study where we would calculate difference scores for each person and compute the average difference score and compare this to 0. If the weight loss program was not effective, the difference will be 0 or close to 0. If the weight loss program is effective, the difference will be significantly different to 0. Paired tests can be used in many situations, including testing the effectiveness of training programs. For a paired or matched test, we calculate difference scores for each individual. One assumption of this test is that the differences are normally distributed. When looking at difference scores, this may involve before and after studies where the individual is tested twice, or it may involve matching that occurs where we're pairing up different things, different people or different things. This example is on the slide and also in your textbook where there's a pairing up of lots of land and testing different fertilizers but controlling conditions such as soil and weather and so on. Therefore, the major distinguishing feature of paired or matched tests is that much of the noise in the study is controlled for, and therefore hopefully any significant difference we find is due to the intervention. Here are the hypotheses for paired tests. Note that as we are computing differences as part of the test, we are comparing the average difference to 0, and the hypotheses relate to the mean difference, μd. If we are interested in assessing a difference, then we run a two-tail test, and the hypotheses are HO μd equals 0 and HA μd does not equal 0. Alternatively, if we are conducting a directional test, the hypotheses differ to this. For the one-tail test, that is a lower tail test, the hypotheses are HO μd is greater than or equal to 0 and HA μd is less than 0. Lastly, for an upper tail one-tail test, the null hypothesis is μd is less than or equal to 0 and for HA μd is greater than 0. Look, this may sound simple, but students often find these the most difficult hypotheses to formulate, and especially when applied to an example. So let me give you an example and work through this. As a manager, I want to test whether sales training is effective. To measure effectiveness, I expect my sales staff to increase their sales as a result of attending training. Sales figures are collected for each staff member 1 week before training and again 1 week after training. Okay, now state the null and alternative hypothesis. It's not easy, is it? First, you need to know how the data were entered. If I tell you the first column has sales for training for before training and the second column has sales after training, you are now able to accurately construct the hypotheses. If we expect sales after training to be higher than sales before training, the alternative hypothesis contains this statement, HA μd less than 0. And the null hypothesis is HO μd greater than or equal to 0. Let's look at the formula and then some examples. Here is the formula to calculate the t statistic for paired or matched samples. You can see that we've got the t, the degrees of freedom, d bar, which is the average difference, subtract the difference we expect in the population, d0, over the standard deviation of the difference scores, over the square root of the sample size. Okay, so here's an example. Have a look at the data. We have data for 40 Starbucks customers. The data are the calorie intake in drinks purchased before and then after the advertisement of calorie information. Because the data are collected for the same person twice, as is a before and after study, it is a paired test. Now here we have the null hypothesis presented. Does this make sense? Maybe think about the alternative hypothesis, which would be stated as HA μd greater than 0. This should make sense because we expect the calorie intake to decrease from time 1 to time 2 as a result of presenting calorie information. Please note we set up hypotheses before collecting data, so don't let the data drive your hypotheses. Your hypotheses are developed from your research question, and in this case we wanted to know if the presentation of calorie information would have a positive impact on consumers and their choice of drinks at Starbucks. Now let's look at the calculations within the data sheet. As you can see, the sum of the different scores is 84. If we divide this number by the sample, which is 40, this will give us our mean difference of 2.1. In the last column, you can see the calculation for the variance of the difference scores. Now here are more calculations. You can see the calculations for D bar, which equals 2.1, then the variance, which equals 66.50. The square root of this number gives us a standard deviation of 8.15. With all these figures, we are then able to calculate the t-statistic, as shown, of 1.63. Next, we need to find our t-critical values from our t-tables. In this case, it is 1.685. As the hypotheses relate to a one-tail upper tower test, this number remains positive. Our decision is not to reject the null hypothesis, as the t-statistic is smaller than the t-critical value. The conclusion, therefore, is that there is not enough evidence to conclude that the average calorie intake for drink purchases has declined after the advertising of the calorie information. Okay, so here's another Starbucks example. This time we are looking at calorie intake of food purchases before and after the advertisement of calorie information. The hypotheses are the same as before. The null hypothesis is presented on the slide. The alternative hypothesis is HA:/μD greater than 0. This makes sense because we expect calorie intake to decrease from time 1 to time 2 as a result of presenting calorie information. Now here is the Excel output to make our decision and draw a conclusion. The t-statistic is 6.7795. We now look at the one-tower test and see the p-value is 2.15 e to the negative 08, meaning that we take the decimal point 8 places to the left, and hence this number is certainly less than alpha of 0.05. Our decision is therefore to reject the null hypothesis. Alternatively, we could have used the critical value of 1.6849. As we are in a one-tail upper tower test, this number remains positive. As our t-statistic is above the t-critical value, we reject the null hypothesis. The conclusion is that there is enough evidence to conclude the average calorie intake for food has declined after the advertising of this calorie information. Well done, everyone.